whole time. So, all right. You all get to listen to me again, which seems like every talk. But I get the very great honor of introducing my friend Ryley. Ryley is an associate professor at the RMC, Royal Military College of Canada, in Kingston, Ontario. And she focuses a lot on the impacts on geotechnical design driven by climate change. So we saw stuff by Jocelyn Haley last year for her CCLT, and we will also hear more about that this year with Ryley. Ryley, going back to, she's been at Queen's. She's also been, was it York? No. Yeah, it was York. And she also co-leads the GeoCore research group at RMC. She has a very big physical lab there that I've gotten to see. She has research supported by the National Defense, NSERC, the Government of the Northwest Territories, and the NSERC. We are getting her 2024 colloquium talk. This is not her first keynote speaker lecture that she had with the CGS. She was also the grad student, and I remember that one there as a very, very entertaining talk. And I mean that in the best way. I generally tend to fall asleep, so I stayed awake during the entire one. So Ryley and me, I like to do the fun facts. Ryley and me go back almost a couple decades now at this point, and one of our favorite conferences, both of us, was attending Serena Ryder at the Grad Club in Queens. And it was in a room probably about the third of this size, and we both tell people about that story. So without any further ado, Ryley, please come on up.
Thank you, Andrea. Okay, so I think I just need to switch over to my slideshow, which I feel like I'm going to do something wrong, perhaps because you're trying to stream this.
Yes. I assume it's up. Oops. Oh, thanks for coming up. You got it? Yeah.
So while this gets set up, maybe I'll ask a couple of questions. So this was a colloquium that I had the honor of giving at the Geo Montreal conference in 2024. Show of hands, was anyone in Montreal? Yeah, a couple. So I won't actually ask you if you came and listened to me, but I will say it looks like a lot of you, this is the first time you're hearing this talk, so that's exciting. Because that's a lot to live up to try on a Monday night at 6:45 to try and keep everyone's interest. So I will do my best. Please let me know if you have questions as I'm going, ask, because otherwise by the time I get to the end, you will have likely forgotten or we'll all be too tired and just be ready to go home. So feel free to ask as I'm going, because then it'll be fresh on your mind. I might move around a bit. Is my mic, can everyone hear me okay? Is that all right? Okay. So as Andrea said, my name is Ryley. I work at the Royal Military College of Canada, which means I have a really neat opportunity to work at a university, but within the Department of National Defense. All of our undergraduate students are in uniform and are part of the CAF, which is really cool. I'm happy to answer questions about that. But most of my research is done with, typical grad students and colleagues, and so that's the work I'm going to talk about today. But I first would just like to take a second to thank, if I can change the slide, certainly the foundation, so the Canadian Foundation for Geotechnical and the CGS. So they're the ones who sponsor this colloquium lecture tour for allowing the colloquium presentation to actually tour across the country and get a chance to come and present to all of those who weren't able to make that annual conference. So I certainly want to thank them for providing me the opportunity to be here. Okay, I'm going to ask just whoever's really good at finding a mouse on a computer screen, if does anyone mind? We're good? Okay, we're good? So I don't have a pointer, so I can't find the mouse on the screen, so we're gonna do the best. I might come up here and point. If I lose, you lose my voice, just let me know. All right, so I asked how many people were there, and how many of you, now I understand now that I can't say who lives in Vancouver because apparently there's like 9,000 cities and townships and jurisdictions. I'm not from BC, so I don't know the area very well, but how many have worked most of your life in southern BC? Okay, how many of you spend lots of time in projects in a greater context across BC? Okay, across Canada? All right, so we've got a wide experience. How many of you have spent time working on projects in permafrost? Okay, so if I'm saying things that are not making sense or tracking, please ask, because it sounds like we have a group of experts here. So I will also turn to some of you who have done a lot of work. One of the things as an academic is I like to think about things a lot, but I don't have the same practice on actually boots on the ground and actually doing a full design job. So that's where I'm going to rely, if sometimes there's questions, to my audience for that. All right, so permafrost in Canada. Here is a very rudimentary map that is showcasing where there's permafrost in Canada, right? So permafrost being at least sort of spanning 50% of our country, and it's ground that remains frozen, sort of below 0 degrees for 2 or more consecutive years is kind of the definition of permafrost. The different shades of blue are really just trying to showcase what we go from sort of sporadic permafrost, where you might have some permafrost on a north-facing slope, for example, all the way further north until you have continuous permafrost, which basically means that everywhere we're going to have permafrost below the ground. And sort of you can see a little bit, you can't see the words, but sort of showcasing how deep the permafrost can be the further north we go and how it gets sort of shallower and more sporadic and discontinuous the further south. So it's all about ground and it's about temperature. And so we can imagine as we think about climate warming scenarios that this is not going to bode well. And I think that this is a fantastic sort of GIF that was drawn that sort of by Greg Fisk, really trying to showcase where we're going to see some of this warming. And we really see that the mid-century isn't looking good for the Arctic. So a lot of the warming that they're projecting is going to be centered around the Arctic and around sort of the northern and to some extent the southern hemisphere. And what does that mean for all that permafrost, right? So part of the questions we're trying to answer at RMC are understanding that we need to understand how changing climate is really going to drive permafrost change. And what will those changes look like? And so sometimes these changes are large and it's what we see in the news, right? We can have examples such as this, where we have the coastline in the Northwest Territories, which is eroding faster than scientists can measure it. So they had some equipment out where they're actually trying to track the coastal erosion. And obviously the equipment was being eroded out to sea. And this is nothing new. This has been ongoing for a long period of time, but it really does demonstrate sort of the large-scale processes and mass wasting that occur when we have these dynamic events. We have the climate's warming, we have ocean which is changing, and we have things like coasts that are eroding. And the Tuktoyaktuk is facing this, right now. We have large mass wasting events. So you have this retrogressive thaw slump. We have this mega slump that's happening. And in this case, it's happening near the Dempster Highway. So you have these large-scale processes that are now going to be impacting the infrastructure that our communities, that our natural resources and our extraction, mining are all reliant on to some degree to actually move people, move resources, move goods. And so when you have large events like this, how do you start to think about how do we manage, how do we mitigate, and how are we going to do this as our ground continues to warm? But sometimes these changes are smaller. Sometimes they're on a much more local scale. And here's an example of such, where we have a culvert which has experienced ice jacking, and we now have a culvert that is actually no longer performing its job, which is to move water from one side of our road to the other. So we've got a failure event that's happening here. And we sometimes just have really small embankment failures that can occur. Again, this is along the Dempster Highway. So the road is still operational, but this is not something that can be sustained as such. So how do we start to think about actually mitigating and adapting our design for some small scale processes that are impacting infrastructure? Okay, so we need to understand how changing climate will drive permafrost change and what will be required for cold regions geotechnical engineering. So when I put together my colloquium talk, rather than sort of spend all my time talking about one specific project, I decided to sort of dabble in a few, which means that I'm going to sort of stay near the surface, but I think that gives better both from a storytelling point of view, but also from keeping everyone's interested for a while. And so one of the things that we're going to start with is just thinking about permafrost and trying to understand what's happening now. And so apart from some of the visual clues which I showed you, you have these large landslides and mass wasting events that happen, or you'll have a culvert that's jacked out the ground. What are signs that we have and how do we actually track what's going on with permafrost? Well, often we're going to do this with ground temperatures. So the first thing I'm going to talk about is how we started to think about permafrost temperatures and those data sets. So we can imagine that tracking and knowing what our ground temperatures would be is going to be important and certainly beneficial when we think about building infrastructure on top of permafrost. But the Arctic, the Canadian Arctic especially, we have very limited thermal databases. And so this is an example from Sharon Smith, who works at the GSC, the Geological Society of Canada. She published this in 2010. And she was trying to highlight where we do actually monitor ground temperatures and have very deep boreholes that will give us a significant data set. But when you look, we can really see there's a couple of transects and a couple of areas of interest, right? The Mackenzie pipeline, gas pipeline, sort of triggered all of those north-south boreholes that were done. There's certainly a lot up in the Mackenzie Delta. So we have areas where we have some good data, but we have a whole vast Arctic and a whole vast tundra where we don't have very much data. Yeah?
What do you mean by deep borehole?
That's a really good question. So a deep borehole is where you're getting sort of down to 50 meters.
50, okay.
Yeah, so that would be some of the deep ones. But if you have a permafrost thermistor cable that's measuring sort of below 15 meters, you'd be really happy. A lot of the ground temperatures are near surface that have been installed because it's so much faster to do. But some of them actually do go down to 50 meters. Yeah. So one of the advantages of working at RMC is sort of our collaborations with the Department of National Defense. And so my colleague Greg Siemens and I have had the opportunity to work with the Department of National Defense on a really unique number of sort of sites across the Canadian Arctic. Does anyone know what these sites are representing? This is the dew lines. This is the distant early warning sites that were installed sort of back in the 1950s as an early warning detection system for incoming air raids. So it spans sort of 3,000 miles across the 70th parallel. It goes from the US, Canada, Greenland, and Iceland. They started to be decommissioned in about the 1990s when the construction of the North Warning System started to be put in place. And part of that decommissioning was you had a whole bunch of materials that were there, a whole bunch of materials, lots of gas that was used to actually keep the sites open. And so what do you do with all of this material and some of the waste that's there? So for a number of these sites, they actually had to bring some of that contaminated waste and contaminated soil south. But for a number of locations, they actually built engineered landfills with waste covers and left the waste material sort of there on site in these engineered cover systems. And so what we're going to do is I'm going to look in at one specific site, sort of what that looks like. So I'm going to jump to Cam, Maine. And at Cam, Maine, there's in fact 3 landfills that were constructed, so A, B, and C. And part of these systems were designed, right? You can imagine you're in the high Arctic and you have landfills, and you'd like if there's any contaminants within your waste, you're going to want to try and keep that frozen, right? So in the 1990s, as they're building these and starting to construct them, that was their plan. And so from a quality control point of view, if you install thermistors into those landfills, you can monitor what the temperatures are doing and hopefully ensure that your waste is staying frozen. And so they did that, and every landfill and every site has a different number of thermistors in different locations. But what I'm going to do is we'll zoom into one of these thermistor cables. And what we get is a set of data over a period of year that we could plot on what's called a trumpet curve, all right? So a trumpet curve is plotting depth on our y-axis temperatures on our x-axis, and every one of those colored lines is the temperature in those 7 meters on a single day. And it plots that 365 times, and what we get is the trumpet curve of the year. And I've highlighted the mean annual and maximum sort of curve in red. So you can sort of start to see the highlights of what this year looks like. In this case, I'm also plotting what the active layer thickness is. So the active layer thickness in permafrost, that's what thaws on an annual basis. So here in, well, I'm going to say Vancouver, and I apologize, we're in Burnaby. Here in Burnaby, what's the frost depth? Is there a frost depth? Do you get any frost? 0.6, okay. So I do a lot of work in Kingston, so I might have a slightly deeper frost depth, right? And so permafrost is just the opposite. Everything below that is going to stay frozen all year to a certain depth, and your active layer is what's actually thawing in the summer. And so we're sort of showcasing that with my black arrow there on the right-hand side. Everyone feeling good about a trumpet curve? All right, that's like lecture 2 in my permafrost course, so we're flying through this. So with a long-term data set, what we can start to see is how our temperatures are changing over time. And so for the year 2004, I've outlined it in blue, and we can sort of march our way through what a data set might look like over, close to a decade of temperatures. So what we can look at is, well, the active layer. So the active layer has certainly increased. There is a portion of soil that has thawed for perhaps the first time in those 8 years. So that has a lot of sort of relevance if I'm thinking about what that material is doing and if I'm still in the cover system. But what this plot also lets us see is that we have our permafrost warming. And so what I'm showing here on the left-hand side, sort of the shift from red to, I guess, the purple ones left there, is that my permafrost temperatures are now warming. And that sort of is the long-term change. That's going to be what's going to be very hard to recover, right, as we see our climate warming. And so grad student Robin Staricki, she's spent the last few years looking at this data set and trying to analyze it from what's happened in 20 years and what's going to happen in the future. So she chose a number of sites sort of spanning across the dew line set and started to plot and look at what the temperatures have told us from the past 20 years. And so some things she's found to date. She plotted the mean annual ground temperature at a depth of 3 meters. And so the mean annual ground temperature is basically what the average temperature was at 3 meters over the course of the entire year. And she's plotted that for 5 sites for a period of 20 years. So what we can take from this is that our mean annual ground temperature at 3 meters is, doing stuff across the Arctic. Some of them are getting warmer, some of them are actually getting a bit colder. We can certainly see this is the reality of data collection and trying to get to remote sites. There's years where we have no data. The thermistor string was cut by an animal. Like this is the reality of what a data set might look like. She also started to look at that active layer and sort of what the active layer depth is doing. And what we can see here is a little more, we can actually take out a little bit more from this. So the Western Arctic sites, those blue dots, blue circles and orange stars, so those are on the west, and we can see that they have much warmer temperatures. We have a much larger active thickness that's happening. And if we start to actually put in some trend lines, we can see that that active layer is increasing over time. Whereas our Eastern Arctic, which is colder, is sort of seeing a very consistent and constant active layer depth. And these are very similar to other large thermal data sets that have been published sort of across Canada and globally. But Robin, being a very eager master's student, said, this is all fine and well, but I would like to know what's going to happen into the future, right? She wants to know, well, what will these temperatures, what will this permafrost be doing 20 years from now, or 40 or 60? And so what she wanted to do was take sort of climate scenarios and future climate scenarios, which is on the left, and couple it with numerical models. And start to actually understand and start to be able to make these predictions or better projections of what our ground temperatures will look like in the future. And she was able to do this because we had, Dr. Siemens and I have had some grad students sort of beating their heads against the wall and a computer during COVID, really trying to fine-tune this thermal modeling process. How many of you spend a lot of time doing thermal modeling? Okay, I see nobody have a hands up and one thumbs down. So let's not spend time talking about how we did this thermal modeling. But Cameron Ross, who's now with BGC, spent his Ph.D. basically trying to come up with calibrated model sets to this dew line data set. And so, you know, he wanted to do what Robin set out to do. I have data, I can calibrate my models, and I can project into the future based on RCP 8.5. And this will be super easy and great. But he got stuck with, how do you start a model? And what temperatures should my model start at? And so he spent the first 2 years trying to think of a spin-up analysis and what the initialization of thermal models in cold and warm permafrost should be. And then he said, great, I now know what temperatures my model should start at across the dew line sites. Now I can march into the future. But he was also still a little bit wrong. And we're not the first people to do this, and we're engineers, so we're not climatologists who are actually trying to do this and doing this in their spheres very well. For example, the New York Times in 2017 had this infographic that they put out. They were obviously focused on Alaska, but they said Alaska's permafrost, shown here in 2010, is no longer permanent. It's starting to thaw. By 2050, much of this frozen ground, a storehouse of ancient carbon, could be gone. And this is what may be lost. This is alarming. When you look at an infographic like this is sending red flags. I haven't yet, but if I were to overlay the infrastructure in Alaska and roads and the pipeline, we would put that all on top of this would be like sending up huge alarm bells. But what's actually going on here is where Cam sort of got stuck on that second part of his modeling. Because what he realized is he couldn't just take his models and march into the future yet. He had to think about how deep his models were going to be and what that bottom thermal condition, that geothermal heat flux, was going to be. And so that was another year of his life, sort of thinking about the practical solution for what do you put as the bottom boundary condition and how deep your models have to be. Okay, so I'm going to try and summarize. That was a lot of numerical modeling, even though I said I wouldn't. Summarize sort of what he found in this case. So here he is with that spin up, that yellow, that's that trumpet curve in the year 2000 at one of these sites. And he's got a model that I'm showing to 100 meters, but it's actually a 1,000 meter model. So you can imagine how much he loved these deep models and how long they took to run. And what he wanted to do was then apply those future climate scenarios onto his model. So the first time he did it at 10 meters, right? 10 meters is a fairly deep model. It's going to be fairly sufficient for some of the things you're going to do. And so the 10 meters is up there in that blue dashed line. And these were the results he got, the trumpet curves he was seeing in the year 2100 under RCP 2.6, which basically means that we're getting no more warming and we're getting better, all the way up to 8.5. And I respect that we've also moved on, now we're on SSPs, but Cam's work was done before, so that's what we're at. So what we can see is that at a depth of 10 meters, if we did a 10 meter model, it's showing us that we basically lost the permafrost. It's gone, right? So that kind of very faded dashed line on 0 degrees is saying we have no more permafrost. But then we said, well, let's check if it's something to do with how deep our models are. So we made him do to a 25 meters. Nothing else changed. He just now had a bottom boundary condition that was 25 meters away. And he ends up with trumpet curves that look like this. And then when we said, well, let's keep going, and he did the models to 1,000 meters, these were the trumpet curves that he was getting. And so if I highlight what that is, that area shaded in blue is permafrost. That is ground that is still frozen. And so by having that deep model, we're actually capturing those hundreds of meters of permafrost in some of these places. And we're capturing that because it takes significant amount of energy to actually drive permafrost towards 0 degree. And so if we have shallow models, we're not using that energy. So obviously that energy just goes to warming it. And so it does beg the question, how deep was this original model? And the first sets of models that they used to actually publish these infographics was a depth of 10 meters. So we can start to see how sort of that deep modeling wants to go. But of course, if I were to ask every student or every consultant that anything that you were going to do from a thermal modeling point of view had to be to a depth of 1,000 meters, nobody would use thermal modeling. And so sort of his next iteration was, how do we make this, and how do we actually keep the models nice and shallow, but apply a flux for our bottom boundary condition? But again, that's more than we want. So, yeah.
Do Permafrost exist 1,000 meters? Or do we?
Yeah, so permafrost, so 1,000 meters is more than I know. So no, so these models, 1,000 meters, they eventually come back and they're warm. So they get above 0 degrees. But we have permafrost depth that's been recorded sort of up to 600 meters is permafrost.
I think they had permafrost at Ragland mine in Quebec down to 750.
750, okay, there you go. So yeah, in some areas the permafrost is extremely deep. All of our 1,000 meter models, that trumpet curve comes back and crosses over the 0 degree. Yeah, but it is like, we are talking about hundreds of meters here sometimes. Yeah, great question. Okay, so we finally figured out how to make models. The question is, well, what do we do with them? And so it's, what Robin did with them is she came and she said, well, I'd like to understand this from a cover system point of view. And so she chose some of these landfills to actually now apply this future climate warming to a very well calibrated numerical model. And so she did an analysis of a waste cover. So here's just sort of a general schematic. We didn't specifically match the design to any specific landfill because that was sort of getting into territory that D&D didn't want us to be that specific about any one landfill. But here we have sort of what the cover layer looks like. We've got some historical waste at a depth below that. And the cover sort of varied between 3 to 4 meters depending on where this landfill was. From those ground temperatures that have been recorded over the last 20 years, we can see that she's plotted 2003 to 2023. And all of these active layer thicknesses, right, so this is the depth to which we've seen thaw, all sit within the cover system. This is great. This is exactly what we want to see. Our cover material is what's going through the freezing and thawing, and our waste is remaining frozen. So this is great. Robin then took that future climate scenarios and applied it to the surface of her models. And in doing so, she was able to see two things. The first is that it depended on where we were, right? So you can remember that earlier I showed that we had different active layers from an eastern and a western Arctic. I'm not going to sort of lead you to which one is which, but here we've got Site A and their cover performance. So for an RCP 4.5, we can see that in 2075, we still have that active layer thickness within our cover system. And if we are looking at sort of our projected 8.5, sort of what we were saying was the worst sort of conditions we could have and the most climate warming and temperature rise that we would be seeing, even then we do have a little bit near the top of our cover where it's just starting to actually thaw into our waste material, but for the most part, the design is still functioning as intended. So that's a good news story. Whereas for Site B, what we get is slightly different. So currently the system is working well, but even under 4.5 scenario, we can see that that active layer is well into the waste by 2100, and it even becomes more extreme for our RCP 8.5. So while this might be a bad case scenario for this landfill, what it does allow us to do is to actually help support D&D when they're going through risk management and which landfills they're going to be addressing and dealing with first, and sort of helping them prioritize those sites. So that's really one of the ways that we're enjoying our sort of applied research, sort of then going in and supporting decision making for the Department of National Defense. Okay. Second application, and sort of ways that we started to use numerical modeling, was for foundations. And so the foundation that I'm going to talk about is something along the Inuvik to Tuktuk Highway. And so this is at Gunny Creek, which is fairly close to Tuck. And this is sort of, what is it, mile marker 131. So yeah, we're getting fairly close to Tuck. And that's sort of an example, sort of that red is showing where this site is. You've actually already seen this site today. So this is the location of this gosh darn culvert. And so this is photo taken in 2011. It was replaced and the similar thing happened. So putting in a new culvert and putting in a new subbase and started doing that was not actually addressing the challenges and the issues they were having. And so what the design ended up looking like in the end, which was constructed in 2021, is a buried concrete arch. So not a bridge, because I learned, so not as a practicing engineer, that's a different word with very different definitions. So I know that I need to call this a buried concrete arch. But there you have it. So you went from that corrugated steel culvert to a very large foundation system. So those arches are built on a foundation system which is ad-freeze piles. They're 15 meters to 18 meters. They were installed sort of, both sides have the same 20 piles per side. So a very robust foundation. And then they have one other thing in this image. So we can't see the piles anymore, that's to be expected. We can certainly see sort of the concrete arch, but there's something else in this photo that we can see. What are we seeing? Thermosiphons. Okay, how many of you have an idea of what thermosiphons are? Okay, so who would like to take a stab at what a thermosiphon is doing in this?
Conducting the cold.
Pardon?
Conducting the cold temperature down.
Yeah, so it's conducting cold temperature down and into the ground. In this case, it's a passive system, right? So we're letting the temperature in the air actually drive that process and happening. And what's really interesting is that this whole construction happened during the height of COVID, and the Northwest Territories was very, very locked down during this whole process. And so the thermosiphons and the thermoprobes and the team that were going to install it showed up 2 days before the go, no-go decision on actually having them be in place here, which for a group of academics who are, doing numerical models, sometimes in their parents' basement, this gave us a really good question. It's like, what happens if they didn't actually show up, and what would happen to this multi-million-dollar arch culvert? So, buried concrete arch. Anyways, so let's take a cross-section of this foundation, and what you can see is sort of the schematic of what's happening. So we've got on the top, you can sort of see that SEBs, those are our surface energy balances, and that sort of is not what we need to be worrying about. But we've got black lines and blue lines. So we've got our ad-freeze piles and those thermoprobes, which are, the thermoprobes are what is actually going to be cooling the ground from our whole thermosiphon system. And so Belosa, a grad student of Dr. Siemens and I, she started to do some numerical modeling to try and understand what the ground temperatures would do at this site over time. And so she was looking at it from a thermoprobe being in place versus the thermoprobes not being in place. So we're going to narrow into this one little region and look at what the temperatures looked like in January 1st, 2024 with no probe. We see the very cold temperatures near the surface, those sort of dark blue, all the way down to some sort of permafrost temperatures of about -5. With a probe, we can see that after 3 years, we have significantly colder temperatures that would be around our ad-freeze pile, which relies on those temperatures to actually maintain that bonding and that strength that you get from the frozen bond. So this is good. This is we're able to actually validate that we can do this kind of numerical modeling and look at what the temperatures would be. She applied those scenarios of warming temperatures of 4.5 and 8.5 to the surface. And with no probe, we have basically lost all of our permafrost, which means that the ad-freeze bond strength that those pile foundations were designed to have is no longer there. But with a probe, we still have sufficient temperatures down sort of that adfreeze pile or just warming beyond it. So we would have had that adfreeze bond strength for a much longer period of time. And so one of the consulting engineers who does a lot of work, sort of especially along the ITH, Ed Hove, we spent a lot of time talking with him about how he designs his adfreeze piles and what sort of his rules are for knowing when your temperatures of permafrost are going to be too warm and you're going to lose that adfreeze bond strength. And so his traditional rule of thumb is being at a depth of 10 meters when your pile is, when that pile temperature in the soil at 10 meters is warmer than -1, you've got problems. So we said, okay, Ed, let's take a look at that. So at that red node, which I'm sort of showing on the left, is a depth on a pile of 10 meters. And if I plot that with no thermal probe into the future, I have a green line. And if we have the thermal probe, I have the blue line. And so what we can see is that with no thermal probe, we likely would have reached a temperature of -1 in, I don't know, about 10 years from now. That's not the best return on investment in terms of your adfreeze bond strength from our pile and your foundations. But with those thermal probes, we're lasting until 2080. One of the benefits of sort of being part of this project from the get-go is that we sent up with the construction group a whole suite of thermistor cables. And so they installed for us those thermistor cables, which are going to measure and monitor temperature over time. And so we've collected that data. So here's an example. This past March, we went up and we actually collected some of the data at Gunny Creek. So here's some graduate students. We're underneath that arch, and we were actually using thermal images to really actually see how well those thermosiphons were working. It was -40, so it was a bit chilly, but the camera is certainly telling us that those thermosiphons are working because they're warmer, so they're exchanging the warmer permafrost temperatures up and bringing that colder air down. And our temperatures at the depth of 10 meters on our thermistor string that's at that pile have been summarized in a 2022 and 2024 plot. And so they are aligning here on our graph. So we haven't actually I need to add 2025, but I haven't yet, so I apologize for that. But this is a good news story. This is telling us that those thermal probes are working. It's validated with that visual thermal image, but this is showing us that providing the system keeps working, these foundations and these adfreeze piles will work for a long period of time. And I know I've spent a lot of time talking about the joys of numerical modeling, and we sort of started off with these large data sets and how much they're important, and it really is. So we have 6 of those piles that are across this foundation system have thermistors that are installed. And so we're actually able to see sort of what that profile looks like from ground temperatures sort of across our foundation system. And it really allows us to see how much influencing sort of that opening of the arch is on that right-hand side. You can see how much warmer those temperatures are going to be. So our numerical models likely, that's not something that we're doing yet. We're not actually therefore incorporating what the air temperature is within that arch and how that's influencing it. But sort of getting this ground temperatures and relaying that together, I think is really valuable. And we're excited to sort of put those two from a field data and our models together. Okay, and the third application is something that sort of Robin Stricky, she's the one that sort of looked at that dew line data, what sort of took her model sideways. And for how many of you have spent time working with climate projections and using those in your design some way, somehow? Okay, so for you in the front audience, have any of you ever tried to look at the snow projections? Okay, I have a kindred friend up here. Snow. It is being projected in the future under the most interesting set of parameters that are quite varied and quite wide and have the hugest, largest, you can imagine, insulative effect on what your ground temperatures are going to do in the future. So we can think about it from like a small scale infrastructure point of view. And we've done that working with the Northwest Territories Geological Survey, where they've done significant work on field investigations on snow compaction. So you have really nice fluffy snow. It's going to keep your ground warm. From a permafrost perspective, that's not what you want. So they go out and actually, if we compact the snow, right, we're going to actually allow that cold air to penetrate, keep our permafrost colder. From an embankment point of view on our roads, that's a good news story. And then, of course, our collaboration with them happened in about 2021, 2022. So Jay Cummings has spent a long time modeling what those compactions would look like in terms of a model. But Robin started to think about, how do those snow projections influence my ground temperatures? And so she spent a long time thinking about that and across the dew line sites. But I'm not going to talk about her results because she's going to be doing those at Geo Manitoba. How many of you are going to be at Geo Manitoba? Okay, so if you're interested in knowing, Robin will be presenting her snow findings at Geo Manitoba, so we'll leave those for there. Okay, so lessons learned from thermal models. There's a lot of really neat ways that we can apply thermal modeling to understand our infrastructure, understand how we need to be adapting our design as we march forward. So, for example, the ad freeze pile asked and raised a lot of good questions. So Ed Hove talks about, -1 degrees at a depth of 10 meters, but there is a lot of bridge locations across the ITH, as just one example, where they have piles and they are assuming that they're going to have that ad freeze bond strength. And so Dr. Siemens is spending time working with our geotechnical centrifuge and looking at actually testing that theory is -1 exactly when that cutoff happens, or is it -2, or perhaps is it only -0.5. We're looking at cover systems and really understanding how waste and contamination is actually going to move through either the cover systems or the waste and landfill. And so working with some of my colleagues at Queen's University, including Kevin Mumford, who has this really neat light transmission technique, where he basically casts a light through a soil and based on the brightness can quantify how saturated the soil is. And so he and I put our heads together and said, well, does it work when something is frozen? And so we had a student, Major Lefebvre, who actually did that. So he looked at, can we actually do light transmission technique, looking at frozen soils, and can we still understand how saturated that soil is? And then we actually spilt LNAPL into that system and watched how contaminant migrates through frozen and unfrozen soil. And so that was a really neat sort of step to us understanding how contaminants will migrate in frozen materials, because often we would classify those, especially in the D&D realm, as if it's frozen, it's not moving. And so we're trying to sort of build on that expertise and sort of help support them there. And then coming back to those large scale processes. And so here's an example, sort of an image in terms of those retrogressive thaw slumps. Some of you might be able to picture and find the person that's in this image, and that sort of puts it in context. So she's in the top right wearing an orange vest pointing, right? That's the scale of sort of what these retrogressive thaw slumps can look like. But using a geotechnical centrifuge at RMC, we're trying to bring those down to a meaningful scale that we can actually reproduce these kinds of events and try and understand what some of the triggering mechanisms are. Trying to understand things like what influence does the moisture content, the salinity, the temperature have for actually triggering these. And so Dr. Siemens and I are co-supervising a PhD candidate, Ozan, who's doing these experiments in the lab. And so geotechnical centrifuge basically allows us to do small scale physical models, spin it up, and it replicates a much larger prototype scale. And so you can see that sort of thaw slump that's getting triggered and happening, and how quickly some of those phases and failures occur. So that's really sort of how we're bringing sort of not only numerical modeling, but sort of bridging in some of that physical modeling as well. All right, how's everyone doing? Yeah? Andrea hasn't fallen asleep yet, so that's a good sign. Okay. So often I spend a little bit of time talking about ice roads, but being in southern BC, I cut that out. I figured, no, does anyone do work on ice roads? Okay, I'll happily show you videos later, but apparently Ice Road Truckers does a fairly good job of showing what a truck on ice looks like. I haven't watched it myself. So I'm just going to end off with talking about some of the work that I've been doing on a railroad. And so how many of you were here for Jocelyn Haley's presentation? Wow, you front row. The rest of you guys. So, yeah, I appreciate it, but the keener, so I don't think there's much replication. But this is a project that 5 of us across universities across Canada are working on. So Jocelyn and myself are 2. We also have Sean Kenny from Carleton, Andy Take from Queens, and then Pascal Roy-Levier, who's really representing the geological sort of science side of things, and she can really help us understand what's happening in terms of the geomorphology. So we're all working together on a project that's looking at a railroad and permafrost, if you can believe it. So here we've got a slide that sort of showcases the rail systems across Canada, and I'm highlighting the ones in red because this is sort of the Hudson's Bay Railroad. It runs from the Paw to Churchill, and then there's another branch up, but it's about 820 kilometers, and it's a very unique piece of rail because if we sort of zone in on that that blue area, and we merge it with a more sophisticated map that I like to show with pencil crayons, but if we sort of merge that, we get the map of permafrost across Canada and where this rail is. How many of you have ever worked on a rail of some type? Front row? Okay, front row. So you can imagine the objective. How many of you have ever been on a train? Awesome. Okay, how many of you have been on a really smooth train? And how many of you have ever been on a bumpy train? Okay, so now picture a bumpy train and put it on ground that's supposed to be frozen, but you have climate change and you have water and you have things changing. You have a railroad that's built on permafrost, and you can imagine the challenges that they face. And so our research is covering all sorts of different aspects of this rail and how it's going to change and adapt, or how it hopefully will change and adapt over the next sort of 50 to 100 years. So what does the site look like? Well, here's an example of the terrain that this railroad is going through. So this is an image taken by Brett Young. He's the general manager of the Hudson's Bay Railway Group, which is sort of an Arctic gateway group. But what do we see? We see thermokarst lake, we see fens, there's peat plateaus, there's certainly some vegetation, the vegetation changes. We have a very dynamic environment. So if we were to drill down, the types of things that we come up would be something like this. So here's a core that Pascal's PhD student Tabitha took. So we probably don't have to be experts in permafrost. What is part of this core? Ice. A huge, massive, segregated ice. So if this is your ground and this is your core, and it's frozen, you're like, amazing. Ice has some pretty good strength. But then it's going to melt, and that ice is going to become water, and that water is going to drain, and then you've got probably a very large void that your train is now operating on top of, right? So you can picture just the challenges that they have. They also have sort of the inverse challenges, is that if they're in this continuous zone, they might get cores like this. But in that discontinuous zone, they might have one bridge pier that's in permafrost and the other which is not in permafrost, which is therefore experiencing what we experience further south, which is frostjacking. And so here we have the Horn Creek Crossing, which is located about mile 420. So it's in the Herkimer subdivision, which is sort of that discontinuous permafrost region of this rail. And it's a 4-bend steel ballast bridge. I don't do structures or bridges, so I might have got those words wrong. But it's located and constructed on these H piles. And we can imagine that it is not the way that they had constructed this bridge. You can see how much frostjacking has occurred. And in fact, at this point, it had experienced 0.5 meter of frostjacking. So this presents some unique challenges. from an operational point of view, they're lucky. It's a ballast bridge. They can actually remove ballast and keep the rail as level as possible. So that's a win in this case. But you can see that this is not the first time this bridge has had challenges. You can see the remnants of piers gone by. So when they constructed this in the sort of early 1900s, they were building them on wood piers to start. This is the third set of piers that have been installed. And it really does make for some interesting questions on why is this happening, what is occurring in the ground, how much water is there for this jacking to happen. And so we have a PhD student, Natalie Arpin, who's doing that. So she's really trying to answer some of those questions. She really is trying to quantify how much this is occurring and so forth. So, there's my frost jacking happening there. Now, from a sort of academic side of view, this is a really cool challenge and a really neat opportunity to understand this. From an operational point of view, this is terrible and you want to deal with this problem. So a year and a half into Natalie's PhD, they did. They fixed the bridge, which was a good news story for HBR. Right, so they now have a beautiful flat bridge, and the idea is that it's going to operate and perform better. So how do they fix this bridge? Yeah, you've got 48 hours to do the job. You're going to jack up the bridge. You're going to chop the pier. You're going to lower the bridge, and you're going to be like, excellent, my job here is done. They know their job is not done forever, but the job is done for now. So that's what it did. From an academic and PhD student point of view, Natalie was pulling her hair out, but then you say, you know what? Not many people get to zero their data. Yeah. And start with data that has been zeroed. So Natalie has a new lease on life where she can say, I know that we're starting at zero and I can now march forward on what's happening to this bridge. And as you would imagine, cutting the piers has not solved the challenge, and there's still extensive frost jacking that's going on. And so she has this with tilt meters, we've got shape arrays, we've got LiDAR. She has instrumented this bridge to really try and understand. We've got thermistor cables. And so that's some of the work she's doing. And again, we'll be at Geo Manitoba presenting some of that work for those who will be there. And last but not least, I'm just going to talk a little bit about something termed sinkholes. And when you talk to Brett, who's a general manager, he says that this is their number one challenge because it basically happens for hundreds of kilometers. And a sinkhole is how they sort of call what a thaw settlement is that's happening under the rail. So you have very strict regulations on what kind of deformations your rail can have. And so when they have that thaw settlement that happens, these sinkholes occur. And this can be have serious implications for just the operation of the rail, slow orders, etc. So when we look at this site, this kind of looks like a nice stretch of rail. I'll sort of draw your attention to this white sort of instrumentation box because it will show up in the next picture. So if we just change where we're taking this picture a little bit and get a little bit lower and closer to the rail, this is what it looks like, okay? And this is actually not the worst bit of track that they have, not by a long shot, but you can see just how much deformation's occurring. So you have this ballast that is going to be shifting and moving with the permafrost underneath is shifting and moving. And so a huge challenge for them to overcome. So a little bit of sort of breaking out what this is going on at this sinkhole is it's really that transition zone between the peat plateau and a low-lying fen, which behave very differently under the same climate conditions, and how they thaw is very different. And so you get these transitions where you have these differential thaw settlements occurring, and you get sort of these excess changes to a specific rail parameter, which we'll talk about here in a second. All right, so just another sort of view on what that sinkhole feature looks like. So what in terms of a rail perspective, you have surface 62, or S62, is basically really defined in regulations with how much deformation it can have at the midpoint of a 62-foot chord. And however much deformation you have really drives how fast your trains can go. So on the HBR, no train is going very fast on a good day, but this really has huge impact on sort of the speed at which you can actually move freight. And so I'm not going to get into the semantics on the left. If you're into trains, we can talk more about it. But we had a graduate student, John Gallagher, who spent some time sort of putting together a framework for looking at these deformations as an instrument to tracking changes in permafrost. And so what you can do here is track what one of these sinkholes might do over time. So this is 1 mile, and this is data that's being collected by HBR. Transport Canada regulations say they have to collect this data every month. And so all of a sudden we have these monthly data sets that go over years that allow us to actually see how things have changed over time. And back in 1987, they did a similar study. So EBA was part of doing a lot of research and work on the Hudson's Bay Railway at this time, and they were counting how many of these defects happened and where the distribution of those sinkholes were with respect to sporadic discontinuous, widespread discontinuous, and then continuous permafrost. So where were these sinkholes happening? In 2022, John was able to plot it, and we can see the shift north. That is a significant change on where these sinkholes are occurring, significant change onto what is happening in terms of permafrost underneath this rail, and really helps identify and explain to HBR why they're having so many maintenance issues in these regions, and allows them to start to project, well, where is this next 50 years going to go? We can also start to monitor a sinkhole over time. So this is sort of 1 data set, 4 data sets. We can see how we get these sinkholes that are exceeding a certain threshold. And what we have labeled here is a class 2 threshold. Basically, that's telling us what kind of speed we can go at that class 2 threshold. But that's the one that HBR really earmarks as the important one. So we've highlighted here in this research. And so you can see that we've now dropped back. So these sinkholes go up and down. And you can imagine that these sinkholes go up and down for 2 reasons. What's one reason?
Maintenance.
Yeah, okay, so that's the second. Yeah, so permafrost might be going. Maintenance, right? You have a sinkhole that's growing. You're going to bring in a maintenance crew. You're going to add ballast. You're going to retamp the rail. You're going to fix it. And so we have these sinkholes that grow and then disappear because they're out there doing maintenance. And so that's exactly it. So if we plotted what that one sinkhole did over time, we can see that sometimes it's getting bigger, 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 and then it drops. And in these cases, it's largely driven by maintenance. And so if we cut out our maintenance time and plot now the cumulative surface 62, what we can start to see is what those changes are in terms of what's happening now because of the permafrost. So we can see how much our surface 62, how much that sinkhole is growing over the course of a year. And in this case, we can say this is really interesting because it's actually decreasing over time. Asks more questions. Is this a permafrost? Is this, they're just getting better at maintenance? This railroad was closed for 18 months and it had a full changeover of the ownership. And so you have a new group who's in there. So at the beginning, they're learning how to do maintenance properly. And ultimately, over the last 4 years have improved. Lots of questions, I guess, come from trying to answer one. We can also start to think about monitoring what happens within 1 mile. And are all those rates the same? And you can imagine that even within 1 mile, where you really are in the same region, the same climate, there's not a whole lot that's going to change in terms of your external factors. You get very different rates of these sinkhole formations. So you really start to understand that the challenges with permafrost and changing temperatures and our climate warming are going to have huge influences on infrastructure such as something like the rail. All is not lost. There's a lot of work that can be done and a lot of things and adaptation and mitigation measures that have been done on this rail alone. So way back in the 1980s, they installed some thermosiphons. And so there's a number of sites further south where they installed thermosiphons to monitor how actually cooling the ground would improve performance over the long period of time. And so those are those sites there. Those were the sites that were experiencing all of those sinkholes back in the 80s. They're older thermosiphons, and they haven't been recharged probably ever. But again, going out with a thermal camera, Arctic Foundation saw that they are still, in fact, many of those thermosiphons in operation and working. So that's a good news story. Another mitigation and adaptation measure was the installation of geocells. So these were used during the flooding that occurred that actually shut down the rail. So they actually used this to help quickly be able to reopen the rail. So in this case, they're not actually designed to try and limit sinkholes, but they were certainly something that's being done to try and so we were using it as, has it actually helped sinkholes at all? We also looked at how much it actually helped sort of the deformations and the embankment stability. And then the third that's been done so far is just the routine maintenance, right? What does actual routine maintenance do, and how is it going to improve the tracks and this Surface 62? And so all of this is sort of being looked at in terms of grouping it together, what's being done, what hasn't, how well is it performed, how well is the thermosiphon still performing. But I'm on slide 132, and Captain Jiwoo will be at Geo Manitoba to present her work, and I don't want to scoop that on her. And so I won't sort of show any of her results right now. But if you're going to be in Manitoba, you can certainly catch her presentation to sort of see how well some of those adaptation and mitigation measures are working from a sinkhole perspective. All right. So the question sort of is how is our infrastructure behaving, and is our infrastructure built to last? There are challenges in permafrost environments and certainly have huge impact on how our infrastructure is going to perform. And these challenges are not going to get easier. They're only going to get harder and more complex, because once we add in a warming climate, we're going to add in additional water. Water tends to be the enemy of permafrost, and it all goes hand in hand. But my hope is that sort of putting together sort of our numerical modeling and trying to understand what's happening from a temperature point of view, trying to see what mitigation and adaptation measures have worked and will continue to work, and trying to really validate that with some physical models along with numerical models and out in the field, that we'll start to get better at understanding and preparing some of our infrastructure, whether it's retrofitting and adapting what's built or whether it's looking into the future. And that if we put our heads together and put pen to paper, and yes, I promised my kids they'd be in this, but if we all sort of work together and sort of think about these large scales processes and try and better understand what's happening on them from a fundamental purpose, that we will be able to build to last. Okay, so with that, I just need to thank, I have a number of sponsors and support and collaborators that have made this research possible. Research certainly costs significant amount of funding to do, especially when you couple it with trying to get into the field in these northern remote locations. So huge thanks to them. But certainly part of the colloquium is sort of trying to talk about sort of the research that you've been doing or the work that you've been doing and sort of looking forward and into the future. And so I certainly am where I am based on some incredible colleagues that I have, and their friendship and mentorship and working with them has meant a significant amount. So I have to say thank you to the people who are on this slide. There's some people here from Vancouver, I believe. But really the work that I've shown you today is really the not blood, sweat, and tears, but joy and love of my graduate students. And so what can't sort of end a talk without giving all of the thanks to them and their work and their dedication to sort of permafrost research. And so a huge thank you to all of my students for all of the work that they've done in this time. So with that, I'd like to say thanks. If we don't have time to talk today, then I'm happy to answer questions at any time. And for those of you who are ever interested in perhaps learning a bit more about permafrost or wanting to go back to school, grad students at RMC don't have to join the military. So that's, but you're allowed to if you'd like to. So certainly reach out if you have any questions at any time. I'm happy to chat more about it. And again, thanks to the VGS for inviting me to be here. And thank you all for coming on a Monday night with beautiful weather. So thanks for being here. Okay, so with that, if you have any, no, I'm seeing no questions, which is great. I'll stick around here. I would like to take the opportunity to close your AGM. Is that what I do now? Oh, no, you don't have to thank me. It's good. This is what you guys did. Thank you. I appreciate coming. And for those of you who are going to be in Manitoba, show of hands again. Okay, I'll see you there. So that's exciting. So I'll see you at all of those talks, right? Robin, Jiwoo, Natalie. Well, I'll see you all there.
I think there's a question here.
Okay, I'd love to answer questions.
I think yeah, we regularly have at the end of the presentation, questions.
Yeah.
Answer session. So I'm fascinated by the photograph you shown, the CSP culvert jacked up. The photo shows the end of the culvert, is it? So the failure mechanism, the embankment settled and lifted up. You said first.
So that for those ones, the culvert, they tend to call it icings, and so they have a lot of trouble with icings. Lots of places, but the ITH, there's a number of locations where the icing is happening, and so in that case, they have water that's flowing that turns into ice, and so that ice just keeps growing and actually just jacks the culvert out. I don't know if they excavated with intent of seeing if it buckled or if it was actually taken out. I don't actually know if there was a geotechnical investigation when they repaired it or not. Looking at, does anyone know? That's a really good question. I don't know if I didn't answer it, but it's a great question. Yeah.
Yeah, when you're looking at the antifreeze piles and you're projecting out the thermosiphons to about 2080, that's like 60-year design life.
Mm-hmm.
Like a lot of time, we're dealing with 75, 100. Was that really taken into consideration for those cases, or is it just, as low as reasonably practical risk type assessment for this type of thing? Or?
Yeah, so in conversations with the engineers who designed it, sort of a 50-year design life for that is probably going to outlast any part of the road that's around it. Right. And so the design life of a 50 years is going to far exceed the road which is leading up to it. Everything will change between now and then. So they were very comfortable with that was what they were looking at.
Right.
I think because there's so much uncertainty with the temperature, there is a different. I'm gonna look to like my understanding is they certainly don't aim to have like a design life of 100 years. Yeah. They're the challenges they're facing right now is Tuck is looking at a relocation, and so because their community is right on the coast and there's coastal erosion, they're going to have to relocate, and so that's sort of their conversation over the next 40 years, and so those are the challenges that are sort of more in the forefront than this. Yeah. Any other questions? No? Okay.
I stayed awake the whole time.
You did. I don't have a prize, but.
Thank you very much. It was a great presentation. And we have, on behalf of VGS, a small token of appreciation.
Thank you so much. No, this is great. Thank you so much. And yeah, I'm here. I'll happily stick around if people have other questions they want to ask, but otherwise I'll look forward to seeing many of you in a couple weeks. That's a great photo of you.
So I just wanted to mention that I did the same thing.